Thanks, Yang, for the introduction. So the aim of my talk was to demonstrate the potential of gVirtualXray in simulating X-ray images accurately and quickly. And I don't know if my talk is needed anymore because you had a few talks already using, you had one talk, but there'll be some more using gVirtualXray. So maybe I don't need to demonstrate that anymore. So we could have a look at one of the last papers I published. I know it's a bit in the medical community, but I think that might be of interest. So we're not going to look at the paper itself, but some code I published. So gVirtualXray is open source, so all of my research is reproducible, and we try to validate the code. So in particular, we took a CT scan of this lungman phantom. So this is this plastic mannequin. So we got a CT scan from the hospital, we segmented it, extracted meshes, and then we can simulate more X-ray images, and we did various things. So if I go back to my slides now, this is a comparison of a simulation on the right-hand side with a radiograph from the hospital. And this is quite annoying because you know that medical manufacturers, they do a lot of post-processing on their images, and you don't actually know how they do it. So we had to do our best to guess what they've done. But we managed to get an accuracy of, so the error is 1.5%, and the correlation, well, it's roughly 99%, and the SSAM 0.94. So we could say that these two images are quite similar. And we can see, like, here it's a fake tumor, and we can see it here as well. So people have been using gVirtualXray primarily in medical VR because that's where I did a lot of research, like as a PhD student, just to train medics. But then some people used it in medical physics. So here, for example, we got a CT scan without respiration, and here with breathing, and we can start to see artifacts, so things here that do not actually exist. One guy in Spain used it a lot to design new medical imaging modality, and basically what he wanted to do is a densitometric radiographic modality. So it's using two energies, like what you've just seen, one low energy, one high energy, and then the trouble with that, you have a higher dose to the patient. You got a much nicer image, higher contrast, but higher dose. So he thought, like, what if we use gVirtualXray to simulate this second energy using a Kinect to reconstruct the surface of the patient? So here is the single energy, and here this is combining the two radiographs, the simulated one with the real one. And, well, you can see if the contrast is better on the right-hand side or on the left-hand side. So nowadays, a lot of people are using it in machine learning, and we saw two talks using simulations already to train deep neural networks. And what's very funny, when you have an open source software, you don't get to know what people do until you do some bibliography. And there was this guy in the US, they took radiographs of basically bags of chips, so fries if you're American, and they simulated also the same thing. And what they wanted to do really is to do some NDT to find the size of chips in potato bags. So it was a very cool application. I never thought about that myself. People have been using it in analyzing denoising algorithms. So because this is basically some kind of ray tracing, there is no noise. We know what the noise should be like. It's a Poisson noise, so we can add it as posteriori. So then you have a ground truth without noise, and then they try different denoising techniques to see how well they work on fluoroscopy images. So fluoroscopy is real-time X-ray images, and they are positive images, so the bones appear black and are white, which is not like what medics do in radiographs. And people have been using it teaching as well. So here it's a guy working at, I guess as a Spanish equivalent of the Open University. It's an online university, and they use Docker to put together things like gVRXray, IBSim-4i from CERN, and so on, to teach particle physics and X-ray imaging to undergrad students. And so the keynote speaker from last year is now using it to teach X-ray imaging in NDT using Jupyter notebooks. So you could use pretty much any kind of computer, laptops, PCs, supercomputers. You can also use cloud computing. Bear in mind that Google is a bit annoying because they keep changing the settings of Google Colab. So it might work one day, and when you come back the next day, it may no longer work, and you have to figure out what's they've done. It's supporting Windows, Linux, and macOS, but bear in mind that I don't have an ARM processor, so I can only support Intel processors. It's written in C++ with OpenGL for GPU programming, so just for speed, but we can use a wide range of scripting languages, and Python is probably very popular. So what you need is an object to scan, and I mostly use surface meshes. Volumetric mesh from Abacus are also supported, but it's a bit experimental. So if you want to use Abacus, you may have to double check with me that it's working well on your simulation. I've often been asked, like, oh, can we do complex geometries? So we could have several meshes of different material, and materials could be basic chemical elements, like, I don't know, carbon. It could be compound, like water, silicon carbide, or much more complex objects or materials such as alloys and mixtures. So depending on the material you use, you have a different attenuation. Here is for the 3 types of materials. So what is a detector? Well, you have 2 types of detectors that are supported: a linear detector, so 1D array of pixels, or flat panels, and they have a position, an orientation, and a resolution. So the API is relatively flexible, so when you have to use a unit, like centimeters or millimeters, well, actually I don't really mind it. The user can specify the units they want to use. So there have been new developments in gVRXray, and I would have solved some of the problems you had in the model this morning. So now we have scintillators. So what are scintillators? It's a very thin layer at the front of the detector that's going to convert the X-rays into visible light. And this is this visible light that the detector will record. All popular materials are supported, so cesium iodide, GADARCs, and sodium iodide. And you can change the thickness as you wish. But this process is far from being perfect. So if you consider this graph here, so we got incident X-rays coming along this ray, and then they may interact with the matter of the scintillator, and you can see here a pattern that's been scattered. So there is a loss of energy. And what does that mean? Well, for a given photon, let's consider energy 20, or maybe I'll go on that side now. So 20, well, we may detect a photon of about 20 keV. But if we go, so I'm looking at the red curve now. If we go over there, for a photon of roughly 250 keV, we will record the same energy. So basically what it means is that we cannot distinguish between certain photons. 20 keV or 250 keV for this scintillator will be recorded in the same way. So how good is the model? So I try to, as much as possible, to validate any development. So a methodology is to use a bomb-proof simulator that you know is working. So I use IBSim-4 from CERN, and it's very popular. So I did some various simulation with various material, various spectra, various scintillators, and we have present three simulations. So gVirtualXray versus gate, with and without scintillator. And what we can see here on the diagonal profile is that it actually matters if you model the scintillator. You've got to change of attenuation here. You don't really see it here in the white area. You don't see it here in the black area. But on that bright square, it really matters. So by using scintillators, you can improve realism. It could matter for training a neural network, right? So again, this process is not perfect, and what you can see, if the X-rays follow this path, they should be detected around here, but because of this scattering, they might be detected on another pixel. So basically what it means, this is some kind of blur, and this is called point spread function, and it works as a convolution filter. So here we got an example of impulse response, or it's not exactly the point spread fraction, we use a line in that case. And we measure that from a real detector. So this is something that has been experimentally designed. So we can see two simulations, one without the impulse response and one with the impulse response. And what you can see is that, well, at the top without is quite sharp. You can see sharp corners in the profile. With you start to have a bit of blur, obviously. And you can see the difference between these two. So again, if you use a realistic impulse response, you can improve your simulations. And this is what will happen on a CT scan. So we use the same response here. A source, it could be a synchrotron. So here it's actually quite easy to model. This is these big facilities. Or it could be an X-ray tube. I don't support linear accelerators for now. So for an X-ray tube, and this is new development, you could specify the tube voltage. And we use two possible backends, SpecPy and XspecGen, and you can set the filtration as well. So filtration is used, so you just basically put plates at the front of the output of the X-ray tube to transform this highly polychromatic spectrum into something that's a bit more monochromatic. Not quite, but it's a lot better. And when you do that, well, you can see that it's actually changed the attenuation that you get. So we have at the bottom the two profiles without filtration, and here in green and red with filtration. And you can see that the model from SpecPy and XspecGen is slightly different. Another thing we could model, this is the focal spot of the X-ray tube, and that introduced more blur. This is called geometrical unsharpness. And this is because the source is not just the point. It's quite small, but it can matter. So here it's again with a point source. And we could have, in that case, a cube. And basically here what we do is to repeat the simulation a few times. So, and then we have this blur. And if you need some new developments, so I've been contacted by a company working on lithium batteries, and they wanted a simulation that matched their experimental setup. They asked me to, well, I want a rectangle. So I started with a square because then it's easier to debug. But you see we have the blur. Then we can have the rectangle, which matches what you will have in an X-ray tube. So they were quite happy with that, but then you're like, yeah, but actually all these rotated, so could you rotate it? So I did rotation a couple of days later. And what we can see when we compare the profiles is that by adding more and more of these components, of these experimental components, you start to have deviation from the original simulation, which is in blue. So we improve the realism. So I've been asked, well, you know, you got this, and there is this new technique called hyperspectral imaging. So far, what you've seen is a CT scan where people take one image. So, by that. For a given CT scan, you got 1 pixel of voxel value. For hyperspectral imaging, they use a different type of detector. They're called photocounting detectors. And basically, they can define energy bands. So you could have one image for, let's say, 0 to 10 keV, 11 to 20 keV, 21 keV to 30 keV, etc., etc., etc. And at the end, you have many, many scans, or many volume, I should say, for one single scan. And that is used for material decomposition. So the bottom row here, I use the same visualization technique, the same values to display them. And what we can see is like for these two material, basically it does not change with the energy. But for this larger cylinder here in red, you can see that by using a different energy, you start to have a different attenuation. And that will mean that we can start to figure out what was the material. So these type of detectors are very, very expensive. So this is very, very niche. But because this is niche, it's very hard to get data. So now we got a way to create that data. So this morning you were saying, oh, we did not have the Poisson noise. I'm afraid that if you do your master project again, that's not sorted. We did it this summer. And why does noise matter? Well, this is because the longer the exposure, the less noise you have. So here, this is 3 CT scans of the same sample. Actually, here, this is the radiographs at different exposure. And we can see that when we increase the exposure, we have less noise. The noise follows a Poisson distribution. The trouble with that, it's a very slow process. And you will need to do that for every single energy in your spectrum. I did it for every single energy, but then, you know, I want something fast, so it's like, can we approximate that? So I did 3 different noise models and try to evaluate these noise models. So again, we have a simulation with Monte Carlo. We're using IBSim-4, and I can set the same number of photos per pixel in both simulations, so that I should have a perfect match. So same parameters in both simulations. And that's how it looks like for a diagonal profile. And what is quite nice, I guess, is that in the white area, it looks like it's matching. In the black area, it looks like it's matching as well. And in the bright square, is what it looks like it's okay. But what I'm going to do now is to select the region of interest in the white area and in this bright square and compare the average pixel value and standard deviation. So this line is for reference. This is with no noise, so you can see the standard deviation is no. So I guess you can say this is the same values here. And when we look at the standard deviation, so that's like 3 digits after the dot, it's actually not that bad. That's for the white area. And for the bright square, you can see that values are comparable for the average pixel value and the standard deviation. And when we look at actual data, so we got experimental data here and simulated data here, it looks like that the absolute error is relatively small. And when we plot a diagonal profile, no, that's the center row actually, you can see that this is a relatively good match. So as a summary, gVirtualXray is a software that you can use on a wide range of computers, and you can now simulate the whole acquisition chain, from the source to the samples to the detector. I've been asked, oh, can you produce imagining artifacts? You could have beam hardening. I've done that in previous years to show some more research work. So I did not include it here, but you could have various artifacts, and you can use it in any application when you need X-ray simulation. So for future work, well, I'd like to add photon scattering. I'd like to add phase contrast. I'm always happy to collaborate. So if you want to use it, well, you can drop me an email. If you need something that is not implemented, well, I'm happy to do that if that's useful. And for actual future work in terms of research, well, one of the big issues you might ask, like, how do we set all the parameters to match an actual device? Well, you'll hear a little bit about that tomorrow because I'll be a UN's talk. So thanks for your attention. This email address could change. I just had an email telling me that I have my new STFC email address, so you don't have to use that one. It's my personal one.
Right, that's fine.